welcome back to this old milling machine. Recently I got a lot of comments under my videos. What about my milling machine? Do I still like it? Do I think it was the right decision to buy it? What did I modify? How did the epoxy adjustment of the column work out? Where did I get the ISO 30 holder? Why am I that good looking? Things like that. So in general, I would say yes, I'm still happy with the milling machine. It was the right machine at the right time for the right money, and it fits the work I do very well. It's not the ideal machine. The ideal machine I would buy a Filmon Picomax 51, for example. A good manual Swiss-made mill drill with a semi-CNC control. But those are 50,000 euros upward. And that's a little bit steep at the moment. It might happen at some point, but not now. So this is the next best thing for me. And I'm not going to buy a used Deckel tool room milling machine because for my purposes they are not ideal. They are very good tool room milling machines, but they are not great at drilling, tapping. For example, you cannot power tap on a Deckel FP1 milling machine because from factory they don't have a spindle reverse. And the quill travel with 60 millimeters is anemic. So no, and replacement parts cost you an arm and a leg. If you shoot the spindle bearings on a Deckel FP1, good luck. You will have to find somebody who has a cylinder grinder and knowledge about spindles. On this machine, that's like if I buy high-end tapered roller bearings, that's maybe 200 euros. So it's easy. I did modifications to the machine, yes, but none of them were really necessary. It's more about my learning experience and just adding that little bit of, you know, just make it nicer. For example, changing the handles here. Again, usually there are some round knobs and I have these off-the-market handles. These are a standard part that you get from Norilem or Misumi. I changed the spindle to ISO 30, which I talked briefly about in my last video. The ISO 30 spindle is a replacement part from Kami machine tools here in Germany. They are a reseller for imported Asian machines, and they stock the complete quill and spindle assembly, and I have a short section about that in picture format. Unfortunately, I didn't film many of the modifications I did in the recent time because I had to do them kind of on a hurry because there was always work coming in and out. So I have pictures and I will do a hopefully decent job of voiceover. Here is the ISO 30 spindle how it arrived from Kami Machine Tools. As you can see, it had drive dogs, but I removed them. I'm not sure if I'm going to put them back or make my own. The original ones are really crusty. In theory, ISO 30 would be plenty strong enough with a threaded drawbar to drive the maximum torque of my milling machine in lowest gear through the taper alone via friction fit without having to rely on the drive dogs. But in a case of a crash, it still could slip. So I'm not sure about that yet. But as you can see, it was quite dirty. But that's it. That's a Chinese OEM part, so I didn't expect too much. Here is the ISO 30 spindle on the left. You can see the slot for a drift to get out a Morse taper tool. They put in the slot for no real reason. I think they used the same casting for the quill like they would on the Morse taper 4 spindle. I will take care of that slot later for a very important reason. On the right is my old Morse taper 4 spindle with a Morse taper 2 reduction in the spindle. The ISO 30 is a little bit longer on the spindle nose. Also for no real apparent reason. You could fit an ISO 30 well within the Morse taper 4 dimension spindle on the right. But for whatever reason they decided to extend the spindle and create a little bit more overhang, but I suspected that it would not make any big difference, and in hindsight it doesn't. I decided to get rid of the slot in the quill housing because this is a way where chips can get their way into the quill and drop down into the lower bearing of the spindle, which is an unshielded, open, tapered roller bearing. So I took a piece of aluminium and I shaped it on the belt sander so it fits into the slot as a snug fit. I ground it slightly tapered so it cannot fall in. Some steel-filled epoxy, very similar to JB Weld, rounded off the whole operation. Just degreased everything and slapped on a good amount of the epoxy. The overhanging epoxy was then filed off and cleaned off, so it's blending perfectly into the surrounding surface of the quill. So another thing that changed is the quill clamp. Normally this machine has a quill clamp here with a split clamping piece that pinches around the quill. And I wasn't the biggest fan of it because it tended to move the quill off center a tiny bit. And it's also not the stiffest way of clamping a quill. So I designed and built a different quill clamp and mounted it to the milling machine, and again, picture show coming. The new clamp arrangement started out with a large chunk of gray cast iron, and I trepanned out the core because I found it wasteful to bore out that much material. In this case I was left over with a nice chunk of cast iron that I can use for another part. This is the trepanning tool I used. It's a 3mm wide cutting high-speed steel tool. I ground this a long time ago for something completely different, but it works nicely as a trepanning tool. My gray cast iron blank was too thick to trepan out the core in one pass, so I went from both sides and left about 0.2mm of material in the center, and the rest was done with a hammer, just beating out the slug in the middle, turning the ID to the exact size of the quill. In the same setup I machined the face of the quill clamp, because this needs to be absolutely perpendicular to the bore. Changing over the clamp from the inside and turning the OD and the face. This is a good example where the strap clamps on top of the vise jaws are very helpful. I didn't want to use any fancy work holding, so I just put the part in the vise and I ever so slightly clamped it in the jaws of the vise. Then I used 2 hold down clamps to pull the part down onto the parallels. This way this was a very secure setup. And I'm using a saw blade to cut part of the clamping slit, the flexure slit, and also I drilled the mounting holes. Different setup now, holding the part vertically to drill and tap the clamping screw hole, and using a slitting saw to cut the clamping segment loose so it's actually able to flex under screw pressure. Our finished product, the completed clamping assembly, it's going to be bolted with 5 screws against the housing of the mill. I used some O-ring stock in the slot of the flexure to prevent chips from making their way into there. I don't want chips in there and then rubbing against the quill. Also, if you look closely in the bore where the quill will ride, I machined a groove, a circular groove, and there is a hole drilled to the outside, and this hooks up to the one-shot oiler. So the quill of this machine is now always lubricated via the one-shot oiler. Test fit against the quill I'm going to use. Now things get a little bit crazy. Of course I need a surface on the casting of the mill head where I can mount the newly designed clamping ring against, because the original surfaces all are unmachined. I had the option to take the head of the mill and either go to a larger manual mill. A friend offered me to use his Bridgeport clone, which has a horizontal spindle. But like any good self-respecting home shop machinist, I decided to try it with an in-house solution first. So I took a router motor. This is a Kress router motor with an ER16 collet, and I cobbled a holder together which consists of a steel plate that's held in the vise and a clamp that holds the router motor to the plate. And that's standing vertically up so the machine can cut itself. The XY table moves the router motor back and forth, and when I drop the head of the mill, I have my C height adjustment. Here we have a close-up of most of the original boss that's formed on the underside of the casting, already machined away. I took a second pass and surfaced a larger area, so I have a completely flat surface for my new clamping ring to bolt on against. This was an absolutely awful process because the chips were more or less directly flying into the operator's face, hence me, but the dust extractor right at the end mill took care of a lot of the fine dust. As you can see, the end mill is sparking out from time to time. That's because I'm running it way too fast. I choose to run the end mill at about 18,000 RPM. It's a 4-flute carbide end mill from Göring, roughing end mill. It really did well, but it wasn't pretty. I took about the depth of cut of 8 millimeters, stepping over maybe 0.1 or 0.2 millimeter. Basically, it's a manual adaptive clearing toolpath. Then it was just a matter of transfer punching the holes from the clamping ring onto the casting of the mill, drilling and tapping and bolting it against the housing. It's basically self-aligning because it's such a close fit on the quill itself. Here's a closer view of the clamping ring in place, already with a Kipp Schnellspannhebel, a Kipp quick action handle. And I have to say I'm very happy how this clamping arrangement came out. It works excellently. It has a very positive clamping action. It doesn't distort the quill sideways at all. And it's also very, very rigid. 10 out of 10 would recommend. So that's the quill clamp and machining away of the original casting. That worked quite well. Then also I did scraping to the machine. I did not really plan on doing scraping on this machine, and but I was retrofitting a one-shot lubrication system. And while I was doing that, I scraped the base, the XY saddle, and also the mounting surface for the Y bearing support. And while I was there, I also modified the Y bearing support and also the X bearing support, because I was not too happy about the 2 axial bearings and no radial bearing in there. So that's another story here. I didn't do a full scraping job on this milling machine. I did the cross slide, the saddle, and the base, the base of the machine, the main casting. So here I'm working on the saddle, checking it for parallelism, and I can tell you that much, it was off by a lot. It was off by probably 70 micron or more from corner to corner, but in an assembled condition, interestingly enough, that didn't have much effect for some reason. Either it twisted the remaining machine into alignment or something else. I can't tell, but I definitely scraped it parallel within 10 micron or less, and also adjusted the angled surfaces of the dovetail. This picture shows the original bearing surface on the underside of the saddle, which runs on the column casting, and as you can see, it's not too crazy good. After like 11 passes with the biax scraper, it already looked way better. A very decent bearing surface. And here is the second side, only scraped for alignment, not for bearing. That's why the bluing is so off. But the numbers are in microns, so we are from 0 to 10 microns over the whole length of the saddle. This will do for this machine. And here is the finished scraped saddle with all the surfaces scraped for bearing, deburred, and ready to be installed back on the milling machine. This is the first time in over 6 years that I take out the bearings from the X-axis screw, and as you can see, the grease has gotten dirty. The bearings are not sealed and there is a tiny gap, and dirt and dust will migrate into those axial bearings. This is the Y-axis screw of my mill. This is the lead screw, fairly nice Acme thread. We have two axial bearings, the bearing shield, and this holds it all together. The way this assembles is, this goes on here, and we have the bearing shield. This drops over the axial bearing on here. Then we have a second axial bearing, and this part goes on here. This also holds the graduated ring, the dial, to give you your axis measurement. And then this part goes on, and it's cross-pinned. There is a roll pin through here, and this works. This is a fairly standard design to axial bearings. Radial is kinda carried by the ID of the bearing block here. I'm not a big fan of this design, not at all, because when you hand crank, you put radial loads on the hand crank, and while an axial bearing can take a little bit of radial load too, it's not ideal. And the bore in here is too big to be a good radial bearing. It has quite a bit of slop on here. That's not too nice. So, and the preloading is basically non-existent because it's a fixed setting by putting this on here and hammering a roll pin through there. There is no preload on these bearings. So what I decided to do, I went on the internet and I ordered a double row angular contact bearing with a solid inner ring. You can get these with a split inner ring, so you can preload it, or you buy these which have a preset from the factory set axial play, and these usually come out at about 1 to 10 microns in this size radial axial play. And being a angular contact bearing, they can carry a lot of side load and axial loads. So this goes on here. These two will go away, these axial bearings. These have spent their life. These are 6 years old and they have seen a lot of hand cranking. So this is a nice drop-in replacement. This goes on here. We might have to give this shaft a little bit of diameter reduction. Just a little bit, so this is a nice press fit on there. We need to bore the bearing shield here, so this can drop in. Needs to be a nice sliding fit with a little bit, with ever so slight proudness of the bearing. The bearing needs to be about maybe 0.02 millimeters above this flange surface. So when you push it up against the casing, the casting of the machine, which I scraped, this holds it firmly in place and it doesn't move axially. And then we put a spacer on here. This goes on here. Hand wheel goes on with a little bit of, we'll give it a little bit of gap. And then we put an axial screw on this, which pulls everything against the inner ring of this dual row angular contact bearing and gives us a very good bearing situation for this piece here. Let's look at the new bearing situation. It's only a round part with center line. this is the screw. The red thing in the center here is the screw, and this thing here is the dual row angular contact bearing already sitting on the end on this little shaft piece here. The green piece, that's the bearing shield, the casting that we bore, so it accepts the bearing. This color, this is the casting of the mill, like this. The green piece pushes the outer ring of the bearing against the casting, clamps it in place firmly, all good to go. Now all we need is one more color. We have our the black part is this black part here. This goes on here, and we need a spacer ring here. So this part pushes up against the inner ring of this bearing and pushes the inner ring against the shoulder. So this clamps the inner ring of the bearing against the shoulder of the screw. And then we just put in a screw from the end, which holds the whole mess together. So let's machine this casting here. We'll put this on a magnetic chuck like this, screw up the OD here, then reclamp it on here with the 6 jaw chuck and bore this out to a close fit for this bearing. I stuck the part on the magnetic chuck and I dialed in the ID of the bore using a small copper drift to knock it around. And now we can take this CNMG lathe tool and true up the OD of the part to run through to the ID of the part. It's probably already pretty good because it was machined, but it's now painted and I don't know how good it's machined, so we're going to do that. That cleaned it up apart from the oiler hole and the 2 rivet holes for the 0 indicator on the dial. I'm probably going to flip the part upside down so I don't see the 2 rivet holes, and I'm going to turn a small plug to go in the hole of the oiler. We don't need the oiler anymore, or grease fitting in that case, because the bearing I'm putting in is lubricated for a lifetime. I'm roughing out the majority of the material with this ISCAR combination insert, drill and boring tool. I'm using this because it has a very robust roughing insert on it. Compared to the large CNMG boring bar that I'm using now that has a finishing insert on it, I do not want to remove a ton of material with this insert because it has a little bit more of a delicate cutting geometry and I don't want to overdo it with it. Okay, we're back at the bench. We're going to assemble this thing. Everything's clean. First we put the bearing in. Dual row angular contact. And we take this thing around, flip it 180 so you see a little bit more. Then we have our feed screw. This goes into the ID of the bearing. It'll take some force, push it all the way down. Then we have a spacer. This is just a piece of DOM tubing parted and faced to length. This goes all the way up to the inner ring of the bearing. Then I'm using one of the rings of the old axial bearing, which is hard and parallel, as a spacer plate. This goes on here because this piece here is weirdly tapered and this bridges this. So this piece goes on, this rides up against the hard ring and the spacer bushing. So this contacts, in theory, the inner ring of the bearing. Next step, hand wheel. And now when we look, the end of the shaft is recessed behind the the hand wheel. Now we put on a washer, which has a small recess board so it centers on here, and a screw which is slightly too small on the head, but it will do here. And when we tighten this screw down, we pull the hand wheel, this piece here, the spacer disc and the tube spacer up against the inner ring of the bearing and lock this whole thing to the bearing together with the feed screw. The bearing itself is not secured in the casting yet. It can move axially. That will change once we mount this up against the casting of the mill. And we forgot the dial in here. We don't really need the dial, but it covers up most of this black piece, which is not the prettiest part. This serves also as a fallback when the gas scales or the DRO itself fails and I absolutely need to machine something now. So then I have this failback here. This screws nice, and this is way nicer than with the axle bearings before. I'm working on the cross slide of the machine and also on the cross slide feed screw. Here I'm checking the mounting surface where the bearing flange. This mounts up against this face, but when I did some routine checks I noticed that the surface is not square in this direction or this direction to the y-axis. Travel means that the farther away the screw goes from the bearing section, the more it bends the screw, which is bad. Leads to uneven wear of the nut and an uneven hand cranking experience. And it feels like it cranks harder the farther you go away from the bearing. Or, depending on the alignment, it gets harder when you crank towards it. So we don't want that. So I'm scraping the surface square and parallel to the travel of the machine. And this is the way I'm checking for alignment. I have a Moore 123 block, which is decent enough in squareness and straightness and parallelism. And I bolted it up against this face with a single screw. And I have an indicator set on my cross slide, and I can use this to check if this face is aligned in this direction. Then I can reorient like this onto the top side of this block. Do the same test again, and I'm within, I'm pretty close already. This is a close-up. Here's the block that's bolted up against this face, and I'm riding the indicator back and forth on this surface. This gives me a pretty good indication of what's happening and allows me to scrape the surface so it's true in both directions to the travel. The scraping print is still very awful, but I wanted to show you something else. This whole surface here on the front of the machine is one surface that has been face milled, but I'm only scraping this small section. So I took a die grinder and I cut a light relief groove with a ball burr. So I'm only scraping the surface. I'm going to retouch the color, the paint on the front face here later, once I'm done with scraping. But this relief allows me to scrape only this and leave this untouched. What I have on here are two vices. One is a Girardi and one is a Holex, and they're basically the same vice, just different branding. Not sure who came first, not sure who makes them originally. Two vices with 120mm wide jaws. I surface ground the jaws on this one to be smooth, and this one still has its V-grooves, which don't do much, but since they work around very nicely, these grooves can be used as an aid for holding small diameter round stock. Not that I need that very often, but it's an option, so I'm not grinding it away. They're aligned on the back jaw to be parallel and in line, and yeah, that's what I use on the vise. One note on the vise handle: originally it comes with an L-shaped handle like you would use to change a tire on a car if you have a blown out tire on the Autobahn. I bought this. This is one of those swivel head wrenches with 19 millimeters, 17 on the other side, removed it, don't need it. And that's very useful because you can use it like this, like a speed handle. Or you can use it like this to put some torque on it. These vises have a coarse adjust. You use an Allen wrench here. And you have a coarse adjust here. You have a steel ball in here. That gets pressed by these two set screws down into these countersinks in the base. That we should keep clear of chips, of course. And the end of this screw just goes in this keyhole here. That's how you quickly adjust the moving jaw. Then you have about maybe 60 millimeters of travel that you can actually use. This design has another benefit. You can remove the jaw very quickly, and for example, if you have a large plate, you can just span it across the vices without having to remove the vices. Just put two larger parallels back here, put the large plate on here, use two strap clamps out here, holding your part without removing the vices. Or use a large T-nut that you can slide in here. Then you can use irregular hold-down hardware in here with a stud and a strap clamp to hold parts directly on the bed of the vise, if you don't want to remove the vise. These vises have a set of threads here in the moving and the fixed jaw, and those are plugged with some set screws. And when you get rid of these, you can put a stud in here. This is all M10. I specifically bought a number of M10 hardware, clamping hardware, for this purpose, and you can use a strap clamp here to give additional hold down strength on a part you're working on. For example, when you cannot put much side load on the part because it's very thin, you can add a little bit of down pressure to keep it secured. And I have, of course, the spherical washers and the spherical ended nuts. I don't buy the sets of clamping hardware. I buy individual pieces. They are not very expensive and good quality, but very much worth it. So we put this on here, put a little bit of backing material under here, so the strap clamp is nice and horizontal. Then you have your hold down in front here. Or you can use this as a vise stop, for example. Many ways to use these threads. Just keep them covered up with a set screw so you don't get all sorts of chips in them. And since I have the vices here on the milling machine and I try not to remove them, the only case where I need to remove them is when I use the large Moore rotary table. But I use that thing maybe once a year, and then it's okay to remove the vices. I put the vices on with some wax between the vices and the table, some LPS3 rust preventive, so I don't get any surprises under the vise. And as I said, I try to keep all my additional tooling set up in a way so I can just drop it in the vices. I have some pictures here. This is a very common example. This is a 5C indexer, similar to the one that Harding made. and I milled two flats on the side of the body, as many people do, and this allows this indexer just to drop in the vise and be ready to use within seconds. Small 150mm magnetic chuck also drops out of the box into the vise. It's small enough. This is the backside of the magnetic chuck with a 123 block bolted to it, or the metric equivalent in this case. And this allows the magnetic chuck to be held at weird angles or bolted to other pieces and then held in a vise or something else. Just as a little side note. And be careful when drilling into a magnetic chuck. There are parts on the inside of the chuck that move. Either be very careful or take it apart. Also very careful, there are some things that you have to consider when you take a magnetic chuck apart. Tom Lipton did a video on that topic. And yeah, don't make me responsible if you ruin your magnetic chuck. This is another example. This is my adjustable angle table. Also drops in the vise. Very quick. This is a no-brainer. I learned this from Robin Renzetti. The flange that mounts the 6-jaw chuck to the lathe has two flats milled and ground onto it, so you can drop it right away into the mill vise. And preferably, in one setup, you can turn your part and then transfer it over to the mill. An example of a part being bolted directly to the bed of the vise with the large T-nut I showed you. And this is just a quick way to clamp stuff down without having to move the vise. Another side note, I prefer a vise that has square sides and where the jaws are not proud of the vise body itself, so you can bolt a 123 block to the side of the vise, and that's automatically square then. Means you can use it to square up parts. And here is an example what you do when you have to clamp down a large piece of plate stock. You just clamp it over the vise. Stack up some blocks, drop your stock onto it, and then you strap clamps, not shown in this picture, to hold it down. No need to remove the vise. One quick word about my vise stop. It's back here. Let's remove it. I like my vise stops as sturdy as possible. I don't like the 3D multi-adjustable vise stops. Those are, in my mind, terrible. I have a spacer screwed into the side of the vise with an M6 thread here, and the other side is, I think, M10. Doesn't really matter. And then I have a very simple stop. Just a piece of flat bar with a long slot for the M6. Screw that holds it to the side of the vise. 6H7 reamed hole in front here. A pinch screw here. This pulls this section together, and I slot it using, like on a shaper, just on a milling machine, use the slotting cutter to slot it from here to give it some meat to pinch on this pin. This is a high-speed steel punch. This is a standard part from Tool and Die, and I ground a spherical end on it on the D-bit grinder. Because with a vise stop, usually you want point contact, so you have a very defined stop. A large contact vise stop can be useful, but not always. So this goes in here. And the stupid scale. And this, with very little torque, pinches this pin very securely. And with a heavy washer, it just bolts to the side of the vise. It's really nothing special. It has some range of adjustment, like in and out, because I cut a slot in here. I can move it up and down depending on how my parallels and my work is set up. I also have different pins for this. I have a large elephant foot stop here. I need this in some cases when I roll something round up against it, just so I have more chance of hitting it. And I have also this here. This is a blade stop. It's just a piece of 1mm spring steel silver solder into the end of a piece of 6mm drill rod, and I use this in here in the vise when I'm holding very small work and can't get in a 6mm pin. So that's the vise stop. Really nothing special about it. It's a simple design. Personally, I like the pinch slot here. That's not going to the outside because it looks neat, but that's it. You could also just slot it through with a slitting saw from the front, but I think this is nicer. And when I don't use it, I just swing it to the back and it's out of the way. One important thing in my mind is how you hold down your vise on your milling machine table. And this is what has proven to be one of the more desirable ways of doing so. This is a clamp that runs the entire width of the table, minus a few millimeters on both ends, like 15. And this gives a lot of rigidity to the vise itself. And the way this works is it sits out here. It has clearance all the way from here to here, and it hooks into the groove of the vise up here. And the screw is moved as close as possible towards the vise, because that way the force of the screw is primarily holding down the vise and not getting pressed onto the mill table. You want to hold the vise, not the clamp onto the table. And as I said, we do this on all the VMCs at work, on the large CNC milling machines, and also on our manual milling machines. This has really proven to be very secure, very rigid, and very safe. Also, it's easy to clean because there are not 5,000 little nooks and crannies where chips can collect. Between the two vices I have a combined strap clamp which holds both vices at the same time and pulls them down in the center again with M6 screw. And what I really wanted to show you, I have some foam, some packaging foam jammed in here just to keep chips and dirt and gunk out. This is a very good idea. Makes it really easy to clean. Yeah. Don't use compressed air to clean your machines, fixtures or tooling. So I hope this cleared up some things about this milling machine. It's still the basic Asian import RF45 style milling machine, like everybody sells them, but it has a bit of it has a little bit of modification. I'm still not getting rid of it. It works just fine. It does what I need. I have a ton of tooling for it, so that's it. That's the RF45 or Optimum MB4 milling machine. Thank you all for watching. Thanks for the ongoing support, and I'll be back.